Great. The recording has just started. We're ready to start chapter 6. So what I wanted to mention was that at this point in the course, there's really, I would say, kind of a break in terms of the material of the course, the content. Up till now, we've spent, I'd say, most of our time probably talking about items related to structure, whether it's the chair flips, whether it's the strain, maybe the stereochemistry from chapter 5, Lewis structures and all that from chapter 1. We spent a lot of time talking about structures and the different sorts of structures you can have in organic molecules and how to think about them. We're going to move now into, I would say, like phase 2 of the course, which is going to be on reactions. So we're going to see our first reactions in this course, and as you will see, good understanding of the structure that we've already gone through will be critical to fully understanding how we do the reactivity as well. So in particular in chapter 6, we're going to be introducing a type of reaction called ionic reactions, and probably, I don't know, a percentage, most reactions that are in organic chemistry, maybe 80%, are what we would call ionic reactions. And ionic reactions are ones where typically you have either starting materials, products, or intermediates that are charged. But the main thing we're going to be looking at is electrons are going to be moving, and they're always going to be moving in pairs. And we have an arrow that we use for showing movement of electron pairs. It's a curly arrow with an arrowhead on one end. This is what we're going to be using a lot going forward. You've seen this arrow before already. We've seen them for acid-base reactions, and you've seen them for resonance structures. We will continue to use these. There's another type of reaction that are not ionic reactions called ionic reactions, and this is a chapter that we usually do towards the end of the course. At this point, I'm not going to promise we will do them, but it will be towards the end. We'll try to squeeze it in. Ionic radical reactions are cool too. Okay, so here's a very simple breakdown, or very simple examples of ionic reactions and radical reactions. So if you just have a molecule, 2 atoms and a bond, and all we're going to do is break that bond apart. There's 2 ways you can go about breaking that bond. One is you can split the 2 atoms apart such that each atom has 1 electron. And this is what we're showing up in the top here, where you see the AB bond. The bond between them is represented as a pair of electrons. 1 electron, the pink one, goes to B, 1 goes to A. And what you end up with is 2 molecules or 2 atoms that have single electrons. They don't have all their electrons paired up. And we saw molecules like this that had single electrons back in chapter 1 when we did some Lewis structures. And we call these things radicals. Notice the curly arrow that we use in this case has only like a half arrowhead. That arrowhead is representing the number of electrons that are moving. So if you have an arrowhead with a full arrowhead on there, you have an arrow with a full arrowhead, this means 2 electrons. If you have a half, that's just 1 electron. The other way you can break a bond is by heterolysis. Heterolysis means you break the bond, but one of the 2 atoms gets both the electrons, and this gives an anion and a cation. I say this is more common. This is probably more common, certainly in this course. You will see many more examples of heterolysis. You can imagine heterolysis being much more common if there's a big electronegativity difference between A and B. In which case, B, if it's more electronegative, would much rather have that negative charge. So you might see an example if you have something like HCl, and you would have H plus and Cl minus. That would be an example of a heterolysis reaction. So we're going to be focusing more on the heterolysis type now. Homolysis we may come back to later in the course. All right, we're going to talk about a number of reactions, and for each reaction, what we're going to do is spend quite a bit of time talking about the mechanism of the reaction. And what the mechanism is basically how the reaction takes place. What is actually going on? What bonds are breaking? What bonds are forming? how this happens in terms of steps. Does it happen all at once? Does it happen one step at a time? And the whole point of learning the mechanisms and understanding the mechanisms is if you understand how the reaction's taking place, you'll understand better under what conditions this reaction can happen or not happen, or if you have something go sideways, if you have something else happen. All of this is much more understandable if you understand the mechanism. Otherwise, if you don't know mechanisms, basically what you're doing is memorizing a huge list of organic reactions and the result. And memorizing reactions, there's millions and millions of reactions that have been done and reported and published, and nobody's got a brain to memorize all of those. So instead, what you do is you look for similarities, and you look how broad classes of molecules will react, and you sort of classify them under what we call their mechanism. And we're going to be doing that quite a bit in this course. So I want you to imagine for a minute that you, let's assume there's no COVID right now, and you wanted to fly to Victoria, BC. If you want to do that, there's a number of ways you could imagine flying there. You drive to Halifax, that's your starting point, and what you're going to do is plot a route to get to Victoria. They actually have flights, or at least they used to, that are direct from Halifax to Victoria. So your plane takes off, flies across Canada, lands in Victoria. That was one step. There's no stopovers, and that's about as direct as you could possibly imagine flying from Halifax to Victoria. You could imagine instead another example where you have, say, a stopover in Montreal. So you fly from Halifax to Montreal, have a stopover, and then you fly from Montreal to Victoria. So that would be a two-step flight, or two-leg flight, I guess we would call them if it's a flight. And you'd have one stopover halfway through. Or you could get a flight like I did once, which was Halifax to Moncton, Moncton to Ottawa. No, Moncton to Montreal, Montreal to Ottawa, Ottawa to Calgary, Calgary to Vancouver, Vancouver to Victoria. Don't book a flight like that. I think I saved $15 by getting that flight when I was a student. I'd rather have given up that $15 and had my life back. So like these flights, chemical reactions can take place similarly. They can happen all at once. They can happen in one step, or they could happen as a sequence of multiple steps, just like a flight. And so here you can see on the screen, I don't know what the starting city is, but if you started here, you could do one flight here, another flight here. You know, there's going to be a number of legs. In this particular case, we have 1, 2, 3, 4, 5 steps, 5 legs. And each city we see, we would call it a stopover if we're flying. In chemical terms, if you have a mechanism that is involved with a number of individual small steps, the stopovers we would call intermediates. So they're, you know, chemical products that you create and then you use up in the next step. Each one of these legs in chemistry we call elementary steps. And you may remember this terminology from first year when we talk about elementary steps in the kinetics chapter. So an elementary step in chemistry basically starts with some chemical species, A, and it goes to some other chemical species, B, through a single step. And that single step, you can represent it. If you think back to the kinetics chapter, it will have an energy barrier for each step. And at the top of that barrier, we have what we call the high energy state. It's called the transition state. Sometimes it's also called the activation complex. Basically what happens, in order to get from A to B, you need to put some energy into A to first of all get it into some higher energy state. And then once it gets past that point, it can kind of fall downhill and create the next product, B. So this is how we would look from a potential energy perspective. This is potential energy, where the potential energy of the system goes up to the transition state and then falls down to B. So if you have a mechanism, it's just a number of these steps in a sequence, one at a time. So here's an example of a mechanism that takes place in 3 steps. How do you know there's 3 steps? Because there's 3 transition states. 1, 2, 3. So A goes through first transition state, creates B. B then goes to C, and then C goes to D. Kind of like refueling our plane. Yeah, I guess that's the activation energy that you need. You need, or the lift, the takeoff, right? You have to your plane has to kind of take off until it gets to its cruising altitude, and then it can continue until it makes B, and it lands. This analogy just, yeah, this analogy doesn't stop, eh? So we call B and C intermediates, or stopovers if they're flights. So B is something that would be created at the start. You know, it would be created as a result of the first step, but then it's consumed kind of right away and forms C. Now, each one of these steps will have a rate associated with it, or a rate constant. And you might remember this very important equation from first year, which I won't get you to use in a mathematical sense, but I'd like you to understand it if possible. K equals AE to the minus EA over RT. Anyone remember this equation? Someone in the chat knows. Arrhenius equation. This means the rate constant for a step is a function of a bunch of other things, but EA, which is activation energy. So the activation energy is the energy from the starting point, A, to the top of the transition state. So this will have a different EA, and C will have a very small EA. So each step has its own EA. Each step will have its own rate constant, and the system has to go through all of these steps to get to the end. Now, when you have multiple steps like this, typically one step will have a slower rate than all the other steps. And if that's the case, we call this a rate determining step. And in this example, B to C is the rate determining step. And we know it's the rate determining step because it has the highest EA. Much higher than this and much higher than this, right? So as a result, the whole reaction will take place at the same rate as that slow step. All the other steps don't really factor in to the rate of the overall reaction. Basically, you could call the rate determining step the bottleneck. Right? A will form B right quick, and it takes a while. The B's built up to form C, and then when C is formed, it can kind of quickly, immediately go to D. So the slow part of that process is B going to C. So that reaction mechanism I just showed you, this one here, and I'm showing this in terms of a potential energy diagram. You know, you can see the steps, you can see the humps, you can see the transition states for every step. The other way to draw this is like this. This is the actual reaction that potential energy diagram was for. And this is a number of chemical steps where we are using curly arrows to show what's happening. We are breaking bonds, we are forming bonds, and we are making new molecules. So I want to focus in for a second on step 1. Step 1, we have an alcohol, right? And we have HCl. HCl is what? It's a strong acid, right? Whenever you do reactions and you see a strong acid in the first step, probably that step is going to be an acid-base reaction where the strong acid reacts with something. And that's what's going on here. This first step we would call an acid-base reaction. You can see the lone pair of electrons on the oxygen has one curly arrow going to the hydrogen. That means we're going to make an OH bond with that lone pair. So you can see in our product, we have the same molecule over again, but we switched one of the lone pairs into an OH bond. At the same time, the HCl bond broke, and those electrons moved on to the chlorine atom. And so we make chloride. That chloride is going to have 4 lone pairs of electrons around it. So this is just a normal acid-base step. This reaction would not look out of place if I drew it in chapter 3. Chapter 3 was the acid-base one. So that's just an ordinary step. But we make this thing. We normally don't think of alcohols as being very good bases, but if you put it in with a strong acid, sure, it'll accept protons from things like HCl. And you make this thing. That actually has a name. This is called an oxonium ion or cation. Oxonium ion or cation is this thing. And that's just anything that has an oxygen with protons and a positive charge. So H3O plus is also an oxonium ion, but we kind of have a special name for that one. We call it hydronium. Okay, so we make this oxonium cation. Then there's a second step here, which is step 2. Once you make this oxonium cation, what happens is that bond breaks. That carbon-oxygen bond breaks. The electron pair moves onto the oxygen. And the oxygen now has 2 lone pairs, and you have a molecule of water. That leaves behind this thing. And that thing has 3 carbons attached to the central carbon, and the central carbon has a positive charge. How many valence electrons does that carbon have? Someone will put it in chat. I know someone's still awake there. There we go, 6. Thank you very much. 6 valence electrons. Because there's 2 in this bond, 2 in this bond, 2 in this bond, and that's it. There's no lone pairs, no single electrons, nothing like that. So we have a name for this kind of molecule, a carbon with 6 valence electrons and positive charge. Anyone remember what those are called? Starts with C. Carbocation. There we go. Some answers are coming in now. So that's correct. This is called a carbocation. And carbocations are quite reactive. They're not very stable. Why? Because they have 6 valence electrons, right? Carbon wants to have 8 valence electrons to satisfy the octet rule. So this thing is, I would say, short-lived. What it will do is react with anything that can give it back its full octet. And lo and behold, we have a chloride ion that we generated way back in step 1, right? It's way back here from step 1, still around. This can come in and it can donate a pair of electrons to the carbon, forming a bond. So this curly arrow here is showing pair of electrons from the chlorine going to the carbon to form a carbon-chlorine bond. And you make this, which we would call an alkyl halide. Okay, so that's good. Now, this gave us our product. Notice that in step 1, we make this oxonium ion. And then in step 2, the oxonium ion reacts away to make something different. So what do we call something like that? I see a hand up from Kimberly. Why don't we give a question?
Yeah, I have a question. Sorry, it's not about what you just said, but at the beginning of step 2, I understand why it's reacting at the beginning of step 1, but at step 2, what's going on there can you just repeat what's happening there? Like, why is it doing something?
Why would it go to make this really high energy thing?
Yeah, like why does it go from what's going on at 2 over to the other side? Like what's... So
what's happening in this step? So you can kind of think of it as you have this molecule, it just breaks in half. and basically a water molecule falls off of it because you have right here H2O.
Mm-hmm.
If it leaves and takes the electron pair that's in that CO bond, you just have a nice, happy, stable water molecule here.
Okay, so it's just happier to do that, so it prefers to do that naturally?
Yep.
Okie dokie. Okay, thanks.
It just breaks off. Yep. And you might say, why would it do that? Because it's higher in energy, right? It's more stable for it to be where it was at the beginning. But this is because this is in room temperature or hotter water. If you're boiling this, these molecules are all bouncing around, colliding with each other. So all it takes is this thing has to be rammed by 3 molecules at once, breaks apart, gets a lot of energy. It'll just happen. So you can have steps that are uphill in energy as long as you are not at absolute zero. So if you have any temperature, like room temperature, these steps can all happen.
Okay, thanks.
Yeah, sure thing. So this oxonium cation that's here is formed in step 1, and then it's consumed in step 2. So we have a name for things that are formed in one step and consumed in another. We would call this an intermediate. Intermediate is this thing, because it's formed in one step and then consumed in the later step. It's not present at the start. It's not present at the end. It's a stopover. Same thing, this carbocation, which I'm circling for the millionth time, it's formed in step 2 and then consumed in step 3. So it is also an intermediate. There's actually one more intermediate in this step, in this reaction, which is chloride. Chloride is formed in step 1 and then it's consumed in step 3. So we would call chloride an intermediate as well. So there's 3 intermediates in this reaction. Each, I guess the first step produces 2 of them. Water we would call a product. This alkyl halide we call a product, and the starting material is this. Okay, so we're going to be looking at a reaction called nucleophilic substitution. And before I get too far into this, what I want to show you is an analogy. Okay, you can hopefully see my screen here. Imagine for a second what do you think this is? It's not a Fisher projection, don't worry. This is a parking lot. Top-down view of a car. This is a truck, okay? You got cars here, and getting sloppier with my cars, but you get the idea. Then over here, we have a few more spots. And the parking lot is full. And let's say the main road is over here, right? And so you are driving your car down here. And you need to park in one of these spots because you have an 830 class, organic chemistry, and you need to spot. But all the spots are filled. So if you think about it, how can you park your car in one of these spots? Unit 6 is not on the midterm. If you need to park your car, doesn't mean you can stop listening though. You still need to know all this crap. It's not crap, it's good stuff. So this car, you want to park it, and you have problems parking it because all the spots are full. So you only have, in my mind, you have 2 options. One is you can you drive in or whatever, and you circle around. Maybe you're going to drive back and forth or whatever, and you wait until somebody comes and parks their car, or gets in their car and drives away. So let's say you're doing that, you're circling around, and this person leaves. As soon as they leave, you can then drive into their spot, and you've parked your car. You're happy. You've got your spot. You didn't inconvenience anybody, and you're on your way, right? So that's one way to do it. I should have made our car pink, just so that you can tell it apart from the others. The other way you could do it is you could just drive really fast, smack into one of those cars, and push it out, right? Push that car right out of the spot so that when you're done, I'm deleting my road here. So then when you're done, this car is out here somewhere with a bent up fender, and you're in the spot. So I'm going to call those two different ways of doing it, right? First one is be patient. We're going to wait for an empty spot. Or number two, to be impatient, we're going to have a collision. We're going to knock it out. Certainly one is a little more aggressive than the other, but both would achieve your goal, which is to put your car in a parking spot. Now, if you were going to do number two, if you're going to collide with another car and knock it out, there's some things to consider there. First of all is, if you have a great big truck full of paving stones, you're not going to try to push that out of the way with your car. Your car is not going to be heavy enough. Your car is going to get crushed, and that truck's not going to move. If it's a motorcycle, yeah, no problem, right? You can hit it, it's going to fly out, and you can easily take that spot. For the empty spot, none of that matters. You just have to wait until something leaves. Doesn't matter what it is that leaves. Doesn't matter how big or small your car is. You can take that spot as well. Well, we're going to be looking at reactions called nucleophilic substitution reactions, which are a lot like this scenario. We have a carbon with a functional group, and the functional group is going to be like a car, and the carbon is going to be like the parking spot. What we want to do is swap that functional group out for something else. So we want that car to leave and a new car to come in. And there's two ways that we can do this. One is we can wait for that group to leave on its own, and then something else comes in and takes its spot, which is option one. Or the second option is you ram into that carbon, knock out the group you want to knock out, and you take its place, take that spot. So we're going to look at both of these, and I want you to imagine it's sort of like this scenario where we're trying to take over this parking spot with our car. This isn't just a funny story. Okay, it's super sunny here now, if you can tell by my weird lighting. Which is nice, the sun's rising over Oak Island. So nucleophilic substitution, what this means is you have a substrate, which is normally an alkyl halide. Not always, but normally an alkyl halide. So R is just some carbon group, like here's an example over here. We have a molecule, it's just a carbon backbone, and on the end it has the bromine. So we're going to think of that carbon as being like the parking space. And currently parked in that space is a bromine atom. What we want to do is replace that bromine atom with the hydroxide. This is your car. And you want to knock the bromide out and take its place. And what this would do, this particular reaction would convert an alkyl halide to an alcohol. So the group that's coming in, that's attacking, we sometimes say, which is knocking out that group, we call this group a nucleophile. Why? Because the bromine has a partial negative charge, the carbon has a partial positive charge, slightly polar bond. That negatively charged oxygen is attracted to the positively charged carbon. So it's attracted to the nucleus, it's attracted to positive charge. Does So that's what's going on in that particular place. The bromine we call the leaving group. Hopefully I don't have to explain that one. It leaves, so it's the leaving group. I've seen someone say it yeets out of there, so I've heard it also called a yeeting group. That's not IUPAC yet, though. We got to lobby IUPAC to make that another alternative name for it. But yeah, yeets out of there. So nucleophile comes in, knocks off the bromine, it takes its place. And if you think back to the analogy with the cars, there's going to be two different ways this can work. Either the bromine leaves on its own and the nucleophile comes in, the OH comes in, or the OH collides and knocks that bromine out. All right, so this is, I think, just describing maybe in more detail what I talked about. Nucleophiles are often negatively charged, like hydroxide, but not always. Sometimes they are neutral molecules, like you see here. Nucleophile is just another name from chapter 1, when we talked in chapter 1 about Lewis acids and Lewis bases. Nucleophile is another name for a Lewis base. If you're wondering why we teach Lewis acids and bases in first year, because we kind of just do it off the side and then we kind of never talk about it again, I'm just going to close my curtains here for a sec. Too bright. There. Yeah, this is why we teach Lewis bases and Lewis acids. Partly, they have other uses as well later on. But yeah, the nucleophile can be negative or neutral. The required factor, though, for a nucleophile is it has to have a lone pair. And we'll be looking at many examples of these, so you don't have to memorize specific things off this slide or anything like that. Okay, so let's look at an example. This is a reaction where you have methyl chloride reacting with hydroxide, and at 60 degrees, this is all in water, you get a substitution. The OH minus replaces the chlorine, to get a molecule of methanol and chloride as products. So you might remember this kind of stuff from first year when we looked in the kinetics chapter at initial rates. And what you do is you do a rate experiment where you vary the concentration of the starting materials. If you vary the concentration of the alkyl halide or vary the concentration of the base, you can repeat this experiment several times and measure the initial rate of reaction. So what we find is if you start with an initial concentration of chloromethane of 0.001 molar, that would be intro 2. And 1 molar sodium hydroxide, we see this particular rate. If we then go ahead and double our concentration of what we call our substrate, our alkyl halide, we double that one and leave hydroxide alone, that leads to a rate that's twice as fast. So you double the rate. That will double the rate by doubling the concentration of CH3Cl. If instead you look at experiment 3, you doubled the hydroxide instead of doubling the methyl chloride, that also doubles the rate. Or you could double them both, and you see a rate that's 4 times. So basically what we find is that doubling the first reactant, doubling the methyl chloride doubles the rate, doubling the hydroxide also doubles the rate. So we could say this reaction is first order in the methyl chloride, first order in hydroxide, which would allow us to develop a rate law like this. Okay, great. I'm not going to ask you to do this. I'm not going to give you this kind. We did this in first year, which is useful, but I'm not going to give you tables like this and ask you to determine rate laws or anything like that. But I want you to know that it's possible, and that at one point in time, at least, you were able to do this. We at least taught it to you. So there we go. We've done our due diligence on our side. What you can see in this case is we have now a rate law. And the rate law, remember before how we said if there's multiple steps, the rate law will be the same as the rate limiting step? Well, this is the rate law for the rate limiting step as well as the overall rate. And what we would say is that this rate has first order methyl chloride, first order hydroxide. That means the elementary step, that is the rate determining step, must involve a collision between these two substances. Starting to sound like the scenario, right, where you have the cars collide, one knocks the other out. So this, yeah, that's by having a rate law that includes both starting materials, that means both starting materials are reacting together in the rate determining step. So this is how this looks. This is exactly what happens. We have a name for this, by the way. It's called SN2. S stands for substitution, N stands for nucleophilic, and 2 means this is a second order reaction. Second order means two things are colliding. Two things are coming together in the rate determining step. So this is what happens. You have your methyl chloride, good old tetrahedral, right? sp3 hybridized carbon. And the hydroxide attacks, and it attacks from behind. We call it a backside attack. And it attacks the carbon, so the OH will form a new bond between the oxygen and the carbon, and it's going to use one of the lone pairs on the oxygen, has two others in order to do that. At the same time, the carbon-chlorine bond breaks. So this is the situation where this is our parking spot, the carbon, the chlorine is the car that's already in it, and the OH minus is your car. And actually, look, the colors even work out. Remember, our car was pink, and the car we're knocking out was blue. I didn't even plan that. That just worked out great. So what's happening here is the OH is being aggressive. It's coming in, it's colliding with the carbon. It's going to just knock out the chloride, and it's almost like pool balls. You know, if you have pool balls on the table where you have, say, the 8 ball, and then you have another ball that's right up against it. This would be the cue ball. No, not a cue ball. Let's give it, I don't know, 14 or something. And you are over here with the cue ball, and you hit into it. What'll happen is the 14 won't move, the new ball will be there, and the 8 will be going off that way. You don't want it to go in a pocket, though, because you'll scratch and lose. But this is kind of what's happening in this situation. The carbon doesn't really go anywhere. The chloride flies off, the OH comes in, you've knocked it out, and in our product, you can see we have the OH on the carbon, and the chloride is now kicked out. See this funny thing we're drawing here in the middle? You can see over here we have this double dagger, call it. That means transition state. So this doesn't look like a real Lewis structure, right? It's got these dashed bonds. You have partial bonds between the oxygen and the carbon, a partial bond between the carbon and the chlorine. Carbon is kind of here making 5 bonds, which it doesn't make, but not really. It's only making a half bond to the oxygen, half bond to the chlorine. This is sort of our attempt to draw this high energy transition state that's halfway between the starting material and the product. So this is kind of showing the OH is approaching, it's starting to form the carbon-oxygen bond, and the carbon-chlorine bond is starting to break. And once you kind of get over that activation barrier, then the CO bond forms fully, the CCl bond breaks fully, and you have your products. So you can imagine if this OH tries to collide with that carbon, and it doesn't have very much energy, and by energy I mean kinetic energy, it's not moving very fast, it might just sort of hit the carbon, but it doesn't have enough energy to knock the chloride out. So it kind of bounces off. Same way as if you were trying to drive a car and knock the other car out of the space, and you were going 2 kilometers an hour and you just nudge the car, you're not going to push it out of the spot. You need to ram it. You need to have some energy to hit that car with. Same thing with a molecule, right? So you need, if you're trying to knock a car out, you need to be going fast. All right. same thing. If that OH wants to attack the carbon, knock out the chloride, it needs to be moving fast. So the way we make molecules move fast is we warm up the solution. We heat it up. So this reaction will happen more frequently and at a higher rate if you heat this reaction up. One other thing that you may have noticed is in the molecule starting out, the CH3, all of the hydrogens are kind of pointing towards the left. I guess you could say those 3 hydrogens in the carbon make a shape that's trigonal pyramidal. What happens is when the OH attacks, it pushes those hydrogens towards the right. And at the transition state, they're kind of halfway pushed to the right. And we would say the carbon and the 3 hydrogens in this case are trigonal planar. It's flat. If you just look at the 3 hydrogens in the carbon, it's flat. And then they continue to push to the right. And in the product, they're trigonal pyramidal again, but they're pointing the other way. They're pointing towards the right. So it's almost like, you know, if you look at the carbon and the 3 hydrogens, it's kind of shaped like an umbrella, right? Where it's a carbon, hydrogen, 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 something like that. And just like an umbrella can invert if it catches the wind, that's what's happening here. That carbon with the 3 hydrogens is inverting as a result of this reaction. We call it an inversion of configuration. And this becomes important if you have chiral centers, because chiral centers, if you do this sort of reaction at a chiral center, you will invert the chiral center. You'll flip the orientation. And the orientation is very important for determining if the molecule is R or S. So we will see examples like this for sure going on. This is the same reaction again, SN2. Remember, it's substitution. In organic chem, we give every mechanism a name, and often the name is a very descriptive word. Like it's substitution, we're substituting the chlorine for the OH. Nucleophilic, nucleophile attacks, and the 2 means bimolecular. Meaning 2 things are colliding with each other. They're smashing into each other. So these are the 2 things that collide. Those would be starting energy here in our potential energy diagram. To make the transition state, it's an uphill in energy. There needs to be activation energy in the form of kinetic energy of the starting materials to get to the transition state. And then once you can get to the transition state, it's all downhill from there, and you make products. And so the OH carbon bond continues to form, and the Cl bond breaks, and the Cl goes away. Perfect. We're doing great. Here's an example of an SN2 reaction. If anyone out there is lactose intolerant, it's the fault of not having enough SN2 reactions in your body. There's a enzyme called lactase, and lactase has a residue on it. We call it a glutamate residue. This R is a huge structure, hundreds and hundreds of atoms, the rest of the enzyme. And what happens is this acts as a nucleophile and does an SN2 on this molecule, which is lactose. Does an SN2. This is like the car that, crashes. It attacks this carbon, and it knocks out this other group. So what that does is it liberates a molecule of glucose. This part comes off and becomes glucose. And now you have the other sugar, the left-hand sugar, here attached to the enzyme. Water can come in, and it can do another SN2. It's a nucleophile. Water has a lone pair. It's all you need for it to be a nucleophile. It can be neutral or negatively charged, like it was at the beginning. Water comes in, it knocks out that group, and now you have a molecule of galactose, and the enzyme is restored back to its original shape. So the rest of this group, what that does is it actually has a pocket, it has receptors that will hydrogen bond with the different OHs and makes it specific for the lactose molecule. So it'll fit in there very nicely. SN2 happens, second SN2 happens, and then we've broken up our lactose into these two separate sugars. So this is the sort of stuff we spend a lot more time on in biochemistry. And, you know, that's why reactions like this are important. It's not just to convert an alkyl halide into an alcohol like we've done so far. It describes many, many reactions that take place in our body, like this one, the hydrolysis of lactose. It explains why the enzyme really speeds that process up and why it's necessary if you want to do these sorts of reactions biochemically. I'm just noticing the time, 9:19. I'll do this slide. Sam, got a question?
Yeah, so like both of the parking lot analogies, they're both nucleophilic substitution reactions.
Yeah.
But the crashing one is the two, like they're both using the nucleophile. The only difference
That's right.
is one is called 2 and one is not.
That's right. So if they collide with each other, that's the SN2.
Okay.
If you had the other one, we didn't have time, obviously, to talk about this yet, but
Okay.
the patient mechanism where you wait for the car to pull out and then you take its empty spot, that's going to be called SN1, and that's what we'll be talking about next time we bring this back up.
Oh, okay.
Sound cool?
Yeah.
All right, I'm going to leave it there. I'm going to knock it into stereospecificity or SN2 because we hit our 9:20 time. But please prepare as well as you can for the midterm. Send me any questions either through Teams or through email. And everyone have a great weekend.
Thank you.
Great. Thanks, everyone. I'm going to go find some treasure now.
Good luck.
Thanks.
Thank you.